Welcome to Part 3 of Foundational Concepts in Semantic Modeling. Part 3 will deal with the Web Ontology Language. In some sense, it will bring together Part 1, which was set theory, and Part 2, which is logic, in order to provide a complete view of semantic modeling. The Web Ontology Language, abbreviated OWL, builds on the Resource Description Framework, or RDF. It also builds upon RDF Schema, or RDFS. OWL's predecessors were DAML, the DARPA Agent Markup Language, and OIL, the Ontology Inference Layer. So when I first heard of OWL, it was a concept, and I read the objectives of the project, and I almost fell off my chair laughing because it seemed like a grandiose objective. I thought it might take decades to achieve, but I was pleasantly surprised, and OWL has been around for a number of years now and has proven at least useful in some domains. So let's talk about important concepts in OWL. Identity is a very important concept in any modeling framework. And in OWL, identity is established by a Uniform Resource Identifier, or URI. The URI syntax must conform to a standard. That is, the URI has required parts. It can't have spaces in it, and so on and so forth. An important concept in OWL is that of a namespace. A namespace is an abstract domain that contains a collection of names. The namespace itself, not surprisingly, is identified by a URI. And then within that namespace, the names are fragment identifiers, or local names, added to the namespace. So we have the namespace URI plus normally a delimiter, the pound sign, and the local name. So for example, the predicate class, we've talked about predicates in predicate logic. The predicate class in RDF, and therefore in OWL, is identified by the namespace, which is this first HTTP URI ending in RDF syntax names NS, the pound sign, and the word or the local name property. So we have the namespace URI, the delimiter, and the local name. Now these URIs are not particularly human-friendly to read or to write, and so a namespace can be given an alias or a prefix, and that makes the URIs much more readable as Q names. So for example, if we define the prefix RDF to represent the namespace, the much longer namespace, then we can write the predicate class as simply RDF : property as a Q name, much more human-friendly. Let's discuss predicates in OWL. There are multiple OWL predicates, all of which are subclasses of RDF property. The OWL object property is a set of predicates whose objects are individuals, members of a class. Or in other words, object property, OWL object property represents relationships between individuals. The OWL data type property is a set of predicates whose objects are data values, numbers, strings, etc. And we might say therefore that OWL data property identifies the characteristics of an individual. Another type of predicate is the OWL annotation property, and these are a set of predicates used to provide human readable annotations on the model. Generally speaking, information captured in OWL annotation property subclasses, subproperties, are not meant to be part of the formal model. They're not meant to be used for inference. Examples of annotation properties include the RDFS label property, which in our controlled English we represent as alias, the RDFS comment property, which we represent in our controlled English as note. Another important concept related to predicates is that of domain and range. If P is a binary predicate, that is, we might have expressions of the form P of xy, then the set of all possible values of x, the first argument to the predicate, is the domain of P. Likewise, if P is a binary predicate and we have P of xy, then the set of all possible values of y, the second argument, is the range of P. In saddle syntax, we can declare the domain and range of a predicate in several different ways. Using again the predicate P with domain x and range y, we can say in saddle x is described by P with values of type y. So we define the domain and the range of P. Or we might say P describes x with values of type y. This is probably a more common way to say it. Or finally, we might say, and in some cases it makes more sense in English, to say P is the relationship between x and y. We could say, for example, that child is a relationship between parent and child. Continuing our domain and range discussion, all domains are classes, that is, subclass of OWL thing. Properties of type OWL object property have a range, which is a class, that is, a subclass of OWL thing. And properties of type OWL data type property have a range, which is an XML schema data type. That could be a primitive data type, that is, an XSD, int, float, string, date, boolean, etc. Or it could be a user-defined data type. And we'll see more examples of those in the future. Properties of type OWL annotation property do not have domain or range in OWL 1.0, which is largely the OWL version that we use in our saddle modeling framework. So, as an exercise, enhance your previous model that you developed in the logic section. Add an RDFS label to each instance of person with their name as it would be normally written in English. Give the properties in the model a domain and a range, and then open and examine the translated OWL model found in the project's OWL models folder to see what the corresponding model looks like in OWL syntaxes. We're going to start by opening our previous model. The first task is to give the instances of person an annotation property, a label, and we'll do this by giving them an alias. So George Washington, the alias would be George Washington. For Martha Dandridge, we might likewise give her an alias, and maybe we'll include her previous married name as part of that alias. So that completes the first part. There are multiple ways that we can add domain and range. We could, for date of birth, we could say, well, date of birth describes person with values of type, and let's say that it's a date. Likewise with wife, we could do the same, but let's change it up a little. Let's add the wife up here in line. So we'll say person is a class, and now we're going to say it's described by, and we're going to say wife with values of type, and here given this what we have for classes in our ontology, we'll just say of type person. So now we've given a domain and range to these two properties. We'll get rid of this. You'll notice that the color of wife and date of birth changed slightly because now they are an OWL data type property and an OWL object type property, which is a darker green than they were before when they had no domain and range, and so they were just RDF properties. We didn't have any way to know whether they were a data type or an OWL type property. So we'll save these. Now in terms of exploring the OWL, let's just look and see what we are currently doing to save them. If I look at my saddle properties, I'm going to enable project-specific settings just so that I can see better what's going on with this project specifically. The OWL model format is RDF-XML abbreviated, and so I'm going to just keep these. Now let's go into our OWL models folder, and here's our logic1.owl, and I want to open this just here with a text editor so I can see it in line. We have a bunch of prefixes defined here for RDF, for OWL, for this current model, for RDFS. We are importing some models, and we'll talk about that more later. These are implicit imports. We didn't explicitly say we were importing anything. We have the class person defined. We have presidents of USA, subclass of person. We have an object property wife with the domain and range both being person. We have a data type property, date of birth, with a range, a domain person, and a range XSD date, XML schema date. And then we have a president of USA, George Washington, so he's an instance of this class. He has a wife property with the object, the person, Martha Dandridge. And we have a label here for Martha Dandridge. We have a date of birth property on George Washington, and we have a label also on George Washington. So that's our complete OWL model in that syntax. Now just for kicks, let's go into properties, and let's change it to be represented in turtle, which is a fairly human-friendly syntax. So we'll apply and close this, and I'm going to clean and build the project in order to rebuild all of the models. And now you'll see that I have a logic.ttl, not a logic.owl. If I open this with a text editor, we now have the same OWL model but in a different syntax. We have the prefixes defined. We have George Washington, that he's a president of USA. He's got a label, he's got a date of birth, he's got a wife. We have presidents of USA, which is a class, a subclass of person, and so on and so forth. So there are a number of serialization syntaxes available in Saddle for saving OWL models in various representations or serializations. Let's talk about n-ary relationships, that is, relationships that have arity greater than 2. In predicate logic, we might have any arity relationships. Suppose that we wanted to represent this, that George Washington and Martha Dandridge Custis were married on January 6th, 1759 at White House Plantation in Kent, what is now Kent County, Virginia. One might represent this in predicate logic with an arity for predicate. We could define marriage to take the arguments husband, wife, date, and location. So in this particular instance, we would have marriage, George Washington, Martha Dandridge, January 5th, 1759, White House Plantation. So consider this question: how can this be represented with binary predicates in OWL? Let's first talk about how we might visualize the solution to this problem as a graph. We want to represent using only binary predicates. So we define the concept of marriage, and if we have an instance of marriage, that instance can have a wife, which could be an instance of woman, a subclass of person. That marriage could have a husband, who would be an instance of a man, a subtype of person, and the marriage might have a date and a location. So we have in this graph represented all of the information in this arity4 predicate using only binary predicates in the graph. To represent this marriage information as an actual OWL model, we're going to create a new saddle file, which we'll call marriage.saddle. And I'm going to start with a person class. I'm going to define a couple of subclasses, man and woman, as types of person. And I'm going to define marriage. It's a class, and we're going to say that it's described by husband with values of type man, described by wife with values of type woman, described by and we're going to say date. That's curious. Described by location with values of type, and for the time being we'll just say of type string. So this is curious. Man, woman. Oh, I see what's wrong. Missing an S. So sometimes the information available, you have to think about it a minute to make sense of it. So the parser tells us that there's no viable alternative in input value. Well, yeah, that's true, there isn't. And as soon as I make it values, everything is hunky-dory. Okay, so now let's define our instances. George Washington is a man, probably all we need for this. Martha Dandridge is a woman. And now we can define our main objective. We can say we have a marriage with husband George Washington, with wife Martha Dandridge, with date, and note that I could get, let's see, 5 January 1759 with location White House Plantation, and we'll leave it at that. So we have created the equivalent of the graph model that we looked at visually by creating this marriage, which has husband George Washington, wife Martha Dandridge, a date, and a location. There are a couple of things worth noting in this solution to the marriage question. First of all, you may have noticed that date is a keyword in the grammar, and if we want to use it as a concept, then we have to escape it with a preceding caret. That tells the parser that this is not the date keyword, this is a user-defined concept within the model. The other thing, which you may have noticed in the graph as well as in the OWL model, we don't have to give everything a name. So when we say a marriage with, we have created an unnamed instance of the marriage class, what is called a blank node in OWL, and we've given it various properties. So a blank node is identified not with a unique URI, but rather with by association with other identified concepts and data values.